Imagine you're handed a stack of hundreds of bills, but you've never seen a counterfeit. You only know the exact security features, paper texture, and ink alignment of genuine currency. Your job is to flag the fake, but you have no examples of what a fake looks like. That is the exact mathematical challenge of unsupervised outlier detection. We want to identify anomalies in a dataset, but we only train our models on a mixture of normal data and hidden outliers, with zero labels to guide us. So how do you teach a system to recognize the unusual when it has never seen it? Recent research has uncovered a surprisingly powerful quirk in how deep learning models train, called the inlier-memorization effect. When you feed a neural network a dataset containing both dense normal patterns and sparse anomalies, something predictable happens during the first few optimization steps. The model prioritizes learning the high-density regions first. It rapidly minimizes reconstruction or prediction error on the inliers. Meanwhile, the scattered outliers barely register in the gradient signal. Their error stays high, not because the model is fundamentally bad at them, but because it simply hasn't allocated capacity to them yet. This creates a temporary but highly exploitable gap between inlier confidence and outlier error. We can use that gap as a detection signal. But why does this happen, and how long does that window actually last? It comes down to the geometry of your feature space and your initialization strategy. Normal data tends to form tight, well-conditioned manifolds. The more compact these clusters, the steeper the local loss gradients around them, which the optimizer naturally follows first. Outliers sit in low-density valleys, far from the dominant curvature. Because they don't contribute significantly to the batch gradient early on, they get pushed to the back burner. Theoretical analysis shows this memorization window scales inversely with the outlier-to-inlier ratio. It also depends heavily on your weight initialization. If your starting weights are too random, the optimization trajectory gets pulled into noise, and the gap collapses before you can extract a signal. You need initialization that already hints at the inlier structure. So how do we stretch that window and make it robust? Researchers have isolated two surprisingly effective interventions. First, don't feed raw features into the model. Transform them into a compact representation space using pre-trained embeddings. This isn't just about dimensionality reduction. It's about feature space compression. By projecting data through a frozen, high-capacity encoder, you strip away task-irrelevant variance, tighten the inlier manifolds, and amplify the signal-to-noise ratio. The model now sees a cleaner optimization landscape. Second, apply exponential moving average to the model weights during the very first training steps. Early on, outlier batches can cause erratic gradient spikes that destabilize the trajectory. EMA smooths those updates, effectively low-pass filtering the optimization path. It keeps the optimizer locked onto the inlier curvature longer, preventing premature convergence to outlier-dominated regions. When you combine representation compression with early training EMA, the inlier memorization window widens significantly. But does this actually hold up under rigorous evaluation? That's where the second piece of the research comes in. Anomaly detection has long suffered from a theoretical flaw called inverse monotonicity. In generative and density-based approaches, the model's likelihood or reconstruction score doesn't always monotonically correlate with the true anomaly level. A point can look slightly unusual to the model but actually be normal, while a true outlier might get a deceptively high likelihood. This breaks the ranking assumption that most detectors rely on, leading to inconsistent precision at high recall. To test whether fixing early training dynamics actually translates to real-world reliability, researchers ran a massive benchmark across 57 diverse datasets, spanning financial transactions, medical time series, network logs, and image collections. They evaluated methods using AUROC for overall separation and AUPRC for precision at high recall, which is critical when anomalies are genuinely rare and false alarms are costly. The results were stark. Traditional isolation forests, local outlier factors, and even several deep generative models showed wildly inconsistent performance. They dominate on one dataset and collapse on another, largely because they didn't account for the geometric dynamics of early training or the inverse monotonicity trap. The new approach, which explicitly aligns preprocessing and initialization with those dynamics, didn't just win on a few cases. It consistently landed at or near the top across both metrics. More importantly, it maintained stable performance across completely different data distributions. That consistency matters because anomaly detection isn't a lab exercise. It's the backbone of fraud prevention, intrusion detection, and early clinical screening. When the underlying algorithm reliably ranks anomalies instead of producing noisy, distribution-dependent scores, the entire downstream system becomes more trustworthy. At its core, this work shifts the focus from architectural complexity to training dynamics. You don't need a deeper network or a more complex loss function to solve unsupervised outlier detection. You need to work with how neural networks actually absorb information. By compressing the feature space, smoothing early gradients, and fixing the theoretical ranking flaws in density estimation, we build detectors that are not only more accurate, but fundamentally more predictable. In high-stakes environments where a single missed anomaly can cascade into a major failure, that kind of reliability isn't just an improvement. It's a requirement.